Good afternoon, good evening, or good morning from wherever you are joining us from today. Welcome to a Microsoft Reactor live stream event. My name is Kaylee, and I'm the event planner for the Redmond Reactor space. Before we kick off the session, I have some housekeeping rules I'd like to run through. Please take a moment to review our code of conduct. We seek to provide a respectful environment for both our audience and presenters. We encourage engagement in the chat, but please be mindful of your commentary and please remain professional and on topic. If you would like to refer back to today's session, you can do so on our Reactor YouTube channel after today's live stream. This session will run for about 1 hour. Please submit your questions through the chat and we will try to answer as many as possible. Additional learning links will be added to the chat during the session. It is now time to begin the session, so I will hand it over to today's speaker.
All right. Thank you. Hi, everyone. Thanks for joining this live stream, and very excited to be here. My name is Viren, and in today's topic, I'm going to talk about some of the architectural patterns and best practices around building distributed services. And we'll focus on a product called Netflix Conductor in terms of how does it kind of help you build some of the services at reliable scale. So let's begin with a quiz, right? The quizzes are always fun. So here is a question, something to think about. And this is a question to every one of you. Are you building distributed applications? I'll give like a few seconds to think about it. It's a pretty binary question, right? Yes or no? So here is kind of a deeper look at it, right? Maybe think about your application architecture. Like, do you use microservices? Do you have stateless functions running in cloud? Things like, for example, Azure functions. You have containers that you use to deploy, short or long-running jobs, and you kind of terminate them once their job is done. You have services that are talking over remote process, right? So you're using gRPC, you're using HTTP, or maybe a very custom protocol. And finally, maybe you are doing asynchronous communication. You are using some sort of event bus, right? And I'm kind of generalizing event bus here, but there's kind of a broad category of technologies that you could use here, right? Things like, for example, Kafka, Azure PubSub, RabbitMQ, old school JMS, any of those things. And of course, the answer is resounding yes if you are using any of those things, right? When you think about all of these things, like it has all the recipes and ingredients for a distributed application, and therefore you are building a distributed application. So if you think about an anatomy of a distributed app, what does it contain? Roughly speaking, right? And this is not definitely a thumb rule or some sort of a kind of guiding kind of principle here. But roughly speaking, if you think about it, right, like if you have two or more components which are deployed independently, you have these components talking over the network. These components have their own life cycle, maybe their own state, and they coordinate using some sort of centralized orchestrator or use some sort of peer-to-peer connectivity. And more importantly, the systems are often eventually consistent, as they could be long-running processes. There could be different databases that are at play, and then eventually they will get into consistent state, but for a brief period, and this period could be anywhere from milliseconds to seconds to even hours before they get into a consensus or a consistent state. And in the end, when you think about collaboration, right, these components are typically owned by different teams, maybe domain specific teams who are responsible for those aspects of the application. Right. So let's just kind of recap, right? Like this is what it looks like, right? You have microservices, you have serverless, you have monolith, legacy monoliths applications, which are ready to be kind of re-architected into microservices or serverless architecture, and they are all talking to each other. And of course, there is the aspect of state, because at the moment you have different services, maybe they have their own individual state about what and how they are doing things. To give you an example, let's say you have a service that is responsible for order management, and you might have a small database that maintains the state of the order. And when you think about things like serverless, like often the question is like, where do I even maintain my state? This is a completely serverless architecture. The other thing about distributed applications is that the failures are part and parcel of them. As the services are talking to each other, things can go wrong, right? Service A is calling service B, and maybe service B is having a downtime. Maybe that network has a problem, somebody changed the firewall rules and now they can't talk to each other. A number of things can go wrong, right? It's very difficult to predict what could go wrong there. But communication failures are one of the norms when you think about distributed applications, right? And this is just one of them. There are a lot more than this that could potentially go wrong. I would highly recommend kind of looking up Fallacies of Distributed Computing if you want to know more. It outlines very nicely in terms of what are the things that we typically take for granted when we are running an application in a very sealed environment. Think like a box, a laptop, or into kind of a single machine, right? The moment you go in the network, in a distributed environment, there are a lot of things that typically we take for granted do not apply. So how do we solve this problem? And one of the most popular method and architectural pattern here is event-driven architecture, right? You try to decouple services, and instead of kind of point-to-point and direct communication between the services, you rely on some sort of message bus, to communicate with each other. And what does it do to you? Like, definitely it helps you kind of avoid some of the problems that we mentioned earlier, right? In terms of how do I ensure that my services that are talking to each other, they can survive failures because they don't longer have to kind of make synchronous calls to each other. Side effect of that also is that now you can have very long running asynchronous flows, which are often required and necessary. Again, think about order management system, right? The order is not going to complete in few milliseconds. It's going to take probably days to complete, and you have to maintain the state somewhere during the entire period of time, and maybe continue to have the entire workflow or the state alive. The other aspect around of event-driven architecture is that it allows you to independently scale services. Now, because services are completely decoupled, let's say you have a very popular service. Let's take a very simple example, right? Let's say you have a service that is responsible for sending out emails. As you can imagine, right, like a lot of applications are going to be using this. That means this service might be a lot more used than many other services, and therefore you can scale that independently. And how does that work? Let's say if we dive deeper into the architecture of an event-driven system that leverages PubSub for point-to-point communication, is that you end up with multiple, typically one or more PubSub systems, right? Maybe one type of system, but multiple instances of it with queues and topics, which are responsible for managing certain parts of the system domain. To give you an example here, right? Let's say, again, going back to the order management system, you could have a system that is responsible for managing all the domain messages, right? So publishing kind of the state of the order, a payment, and things like that. That could be a system that is holding the queues and topics for all the system level stuff. Things like, for example, general purpose things like, say, sending out emails or generating PDFs out of the text, right? And things like that. And typically different teams would manage this depending upon what part of the system they own, and they will be responsible for managing scaling and things like that. And the way components talk to each other is by publish subscribe, right? Take for example, when the order checkout is completed, you need to make a payment. You can publish a message to charge the credit card into the bus, and the service that is responsible for charging credit card is listening over the PubSub message, subscribe to that message. Message has all the right information about what needs to be done, the credit card information and whatever not. Maybe it's encrypted, maybe it's in a database somewhere, but it has the right information. It takes the information, does the job, and then it will publish the message back into the queue with right amount of information. And you would also encode the kind of routing, right? And this is an interesting one. We'll dive a little bit deeper into that also in the subsequent slides. But how do you know that what needs to be done next, after, let's say, you have charged the credit card? Do I send out an email? What do I do? So maybe there is probably going to be somewhere some code that is written that takes care of doing that. And of course, every app, every component has to have and typically maintains a small database that contains the state. So what needs to be done, where you are in the process, and things like that. So that brings to another interesting topic, which is the kind of key focus for this talk is around distributed monoliths. What is a distributed monolith? Let's ask. So we all kind of think about monoliths as one single stack application that contains everything, all the code. It's not just source code, but also like the how it is deployed and how it operates and things like that. So again, going back to the order management system, the entire order processing, everything is into a single application, and you don't scale independently, but you scale the entire app if required, right? Which is where you start to break down the monolith into more microservices and more modular architecture for all the things that we have talked about earlier. Now, often that leads to kind of a distributed monolith. And what is a distributed monolith, you might ask? So here are some of the things that that kind of are the characteristics, or what you would call it, like a smoking gun, right? When you think about distributed monoliths, one is service calls are bidirectional, as in like service A is calling service B, and then service B calls back into service A, maybe not on the same wire, but like through a pub subsystem or something like that, right? The other piece, which is around the state management. So there are two kinds of state here, right? If you think about in a system, you have a state for the component. So if I am responsible for, let's take for example a banking application, I have a component that is responsible for a very simple thing, which is to route the payment. So you give me the payment instructions, I will route it to the right system. All I'm doing is that's just that, right? How do I know that, like when I got the message, I have done the routing, if my routing is completed or not? That's all I care about it, right? So I have to maintain that state somewhere in my system, so that, like, let's say if my system goes down and brings up online, I know where was I in the previous transaction, where did I left off, and where should I continue forward. So that's one component level state. The second state is the overall application state. So if you think about, let's say, going back to order management, what's the state of my order that user has placed? Now that state, if you think about it, right, it's not going to be in a single database. There are different components and each one has its own state. Someone has to maintain the overall status, right? And then it starts to get distributed across different databases. The third piece is an interesting one, which is, we talked about it earlier, right? Like, how do you know that once you have charged the credit card, what is the next step that needs to be done? And this is where, what if, for example, when you charge a credit card, you have service A or service B that needs to be used, right? Depending upon if you are just using A/B testing, or there's a new version of the service. So then often what happens is that there is some sort of metadata in the message that contains information about how the message should be processed, what version to use, or what should be the next step to be done, saying that, okay, once you do the credit card payment, you should put a message into another queue called, let's say, order dispatch, so that order dispatch service can take from that point onwards. Now, if you think a little bit deeper into that, right, now what starts to happen is that, like, your entire routing is going to start getting distributed across different small components. So there's not one place where the overall state, but rather every component has some logic around, once I'm done, what should I do next? Or it's part of the message. And then, whoever puts the message knows about what next should be done. So that's, I would call it as like, tight coupling, even though services are deployed completely differently. And supposed to be loosely coupled, they start to have tight coupling between the versions and their routing and implementation. The next step is essentially lockstep deployment, which is, if services are talking to each other, and this often happens when there is no a message bus or queue system in between, which is that, like, I'm always making a synchronous call to a service, and if the service is down, I'm going to have a problem. Like, what do I do next? Do I fail? But I might be one of the components in the entire service call, right? Like, there it starts to have a cascading failures, which means that, like, every time there's a deployment that needs to be done, some sort of state of so to speak, emergency is declared, like, hey, we are doing a deployment, nobody does anything, or you deploy everything together when there are contract changes and things like that. So it starts to kind of create a lockstep deployments. And we talked about downtimes, right? And to avoid some of these problems, you start to rely on a queue or a message broker. But now what happens is that that starts to become a single point of failure. What if that system goes down? Then the entire world basically stops. And finally, depending upon the previous point, if you are leveraging a message broker that is very tightly coupled to a particular technology. So take, for example, let's say you are using JMS. Now we are stuck to JVM based ecosystem, unless you kind of create some sort of abstractions on top of it. So that starts to kind of create issues where in today's world we are seeing more and more proliferation of polyglot development environments, right? People are using languages that make sense for the kind of job that you are doing. All of these things essentially drives the rise to the distributed monolith. So we talked about this, but what's the problem with that, right? You might ask. So there are a few problems that you can see with distributed monoliths and rise in the operational complexity. So one is, if you think about it, right, when you think about the life cycle of an application, there is the initial part of figuring out what needs to be built, right? This is where your product managers, business analysts come into picture, deciding the overall kind of flows of the applications. Second part is actually building the app. Us engineers and developers sitting down, writing code, testing it out, making sure that it meets the specs that is written. And then what happens after the application is built, right? It's deployed, often handed over to SREs for runtime and operations team for managing the day-to-day stuff, right? Like, we are not going to sit around looking at, hey, what happened to my order number 123, why it was not dispatched, why is it stuck. We don't want to do that. There are probably better things to do, maybe build another app. But what tends to happen is that that is often overlooked aspect of building applications is, how do you handle 4-day 100 scenarios. And more, if you think about a distributed monolith, it becomes harder for operations teams to kind of figure out what's happening, especially when things go wrong. And it comes in two different flavors, right? So one is when things go wrong. Take, for example, there's a customer complaint about order not shipped yet. How do you know what's the current state of the order? Now you have to build very bespoke tooling for someone to kind of be able to kind of look at the order status, query a distributed state of databases from different components to figure out, or maybe you use some sort of CQRS or CDC system to capture the event stream, put it into another database. Now you have infrastructure complexities and more infra that you need to maintain, which also means increased cost of operations and ownership, all of those things, right? Not to mention, now you have to build this custom tooling that needs to be handled. That's for the operations team. But what about engineers and developers? When things go wrong, how do you know what went wrong, where it went wrong, right? It increases your debugging time. When things go wrong, now you have 100 different applications to kind of go and debug through, maybe thousands of different containers or machines where any of these things could have run, and that starts to become challenging, right? Now, the other aspect of any business is that businesses are not static. Hopefully, they are constantly evolving, right? Let's say in an order management system, my system could be evolving pretty much all the time, right? Like, we are experimenting with new flows, maybe new discount processes, maybe new machine learning model, right? AI is a pretty big hype these days. What if I'm experimenting with an AI model to find out how much discount should be given to a customer? And oftentimes product managers want to know what's the current state of the system, like how do we do the order management system, what are the opportunities where I can improvise, I can improve my conversion rate, I can improve my delivery times and whatever not, right? Which means that you got to start documenting the current flows, and the moment something changes, you have a week to make a change and release into production. Documentation is often given the lowest possible priority, and then things start to become it start to differ from the reality, right? Your documentation goes out of date the moment it is written. So all of those things makes it much harder the moment you have a kind of a distributed monolith. And you start to think, right, the good old days of monoliths were better because everything was in one place. I could just look at the code and see what was going on. And so what creates a distributed monolith? So these are some of the patterns, right? um, Again, I think we have gone through this, but just to go a very high level, the moment you have kind of very strict reliance on specific messaging system, when you have lack of versioning, and versioning typically means like writing if then else in the code, when your routing is hard coded in the application flow, this is all going to start building distributed monoliths. And oftentimes you need to have some sort of strict ordering in terms of how things are wired up, and you start to build and leverage on distributed locking systems. They all start to create distributed monoliths. All right, so we talked enough about distributed monoliths. Hopefully kind of it gives you an idea as to, just to kind of recap, right? We talked about event driven systems, how that kind of leads into distributed monoliths if not designed carefully. But there has to be a way, right? There has to be a way to kind of avoid that, like and still kind of not fall back into the monoliths, and get all the benefits of a distributed system. So one and these are some of the kind of lessons that I have learned over the years, things that we have experienced running systems in production. One is designed for both synchronous and asynchronous communication, and this is important because some of the systems are going to be low latency systems, and if the entire system is relying on the asynchronous communication, the latencies in the asynchronous communications are not going to be as good as synchronous, right? And that starts to create other issues. So that's the number one thing. And by the way, this is not in a particular order, these are all important things. Second is, instead of kind of using a peer-to-peer coordination system, right, where every component knows about what needs to be done next, how to handle failure and all of those things, leverage an orchestrator. And this is something that I learned very hard way by operating peer-to-peer systems in production environment for a while, getting burnt, and then finally understanding that orchestrator is probably the better way to do things. And that also leads to the next point, right, which is build services which are very independent from application flows. So true to the nature of serverless, right, where you have functions which are responsible for doing one thing and one thing alone, focusing on that, right? Idempotency, single responsibility principle, stateless nature, right? You could maintain a state of your own small little processing, but not the overall application flow inside the service. And again, if you avoid writing routing logic in the code, that solves a number of problems. And last but not the least is designed for failures. This is one area where Netflix invested very heavily, built the entire chaos engineering principles, build systems that can survive the army of chaos monkeys. But if you realize that you are building systems where you have to build and run annual disaster recovery exercises, I don't know how many of you remember this, but or have been part of this or are still part of that, is if you are doing once a year, twice a year, or every quarter, right, a DR exercise, that means the systems are not designed for failures. That means systems are designed for availability. That's one thing in a distributed application environment is not guaranteed, and it just creates more maintenance efforts, more pain down the line. So we talked about service orchestration. Of course, this is not a new concept. Orchestration has been there from for the last many years, right? Decades probably. How does that help? And if you think about orchestrator, right, with an orchestration pattern, right, something like a saga pattern, you have an application with multiple components that are responsible for implementing one specific application flow. So take, for example, let's say you have a checkout flow that you are building, and it requires multiple different services. Now, instead of all services talking to each other in a mesh kind of a fashion, you would leverage an orchestrator where an inventory check service job is to get a request, check for inventory for a particular item of and in this much quantity, and respond back with yes or no answer, probably, and that's it, nothing else. And who is using that service? Is it somebody just checking, or and you are using that in a web page to see how much inventory is left there, so you can say, hey, hurry, only last two pieces remaining. You might have seen that on some of the uh, kind of e-commerce apps. Or maybe it's part of the checkout process to verify that, like, you do still have the inventory remaining when the checkout process starts, before you actually go ahead and charge the credit card payment and all of these things. Now, this is all taken care by orchestrator. The services are completely decoupled. They have no idea that they are part of checkout process or an application that is building the UI for a particular item, and none of those things, right? They are very much single responsibility, as I mentioned, and nothing else. And they have their own database. Maybe inventory check service has a database of inventory, and it can query database and give you the answer. But it does not know what needs to happen next, what's happening. Orchestrator takes care of all of those things. And if the service is down, potentially orchestrators can retry. It can wait for some time if the service is not available completely before giving up and responding back with a failure. So that brings another point, which is, what is a good orchestrator? You can, of course, write this whole thing inside a simple code and build your own orchestrator. That's pretty easy. But let's say if you were to build an orchestration service, a platform that allows you to kind of orchestrate different flows across your entire org, what is it that you are looking for? And we started asking these questions when we were thinking about how do we solve the problems that we had mentioned with a pub sub and peer-to-peer systems. So the number one I would like to highlight is no single point of failure. And this is often, like, when every time you look at and read about orchestrator, this comes up at the number one thing, right? If I go back to a slide, this entire checkout process is now relying on the orchestrator, which means the availability of my application is directly proportionate to the availability of my orchestrator. It cannot go down. So it cannot be a single point of failure. It has to be fully distributed. Number two, orchestrator relies on queues. So it can do long running flows, asynchronous flows, and guarantees with the deliveries, right? So you want to have an orchestrator which has queues with delivery guarantees, ideally at least once delivery semantics. I would love to see exactly once. That may not be necessary all the time and might be too much. The other piece is, it should be able to implement well-known orchestration or service discovery patterns, right? Things like, for example, service circuit breakers, being able to discover the services. That makes it easy to kind of build applications. The next point is, again, going back to the first one, right? Design for failures. Don't design for availability, design for failures, that orchestrator can actually go down and your entire state does not get lost. It continues to move forward, and it continues to maintain the SLA that your organization, your company, your application needs. And finally, versioning. This is an important part, often overlooked. Not much thought kind of typically goes into it until you reach the version 10 of the service, that holy crap, I have like 10 nested if conditions here. How do I simplify this? So orchestrator should be able to kind of take care of the versioning. If I go back to the slide here, imagine I have two different versions of a checkout flow. There is a version that is running in production. This is how it looks like. And there could be another version that, instead of using a shipping service, maybe it is using a third-party shipping service. So it's a slight change here, but it's a different checkout flow altogether, because it does not use the same process. So instead of now figuring out where do I write the code to do this A versus B, the orchestrator should be able to do that, and ideally with a new version of the service, saying that when I do a checkout, if I'm running an experiment, and if Viren is part of the experimentation audience, it should use the version 2 of the orchestration service and test with a new type of uh, shipping service. And finally, if I have an orchestrator that knows everything about everything, I should be able to document flows automatically, right? I should not have to now have another Confluence page or a wiki page with the entire documentation, everything. It should be self-documenting. The moment I change something, let's say if I go back here and my notification service goes from purely being an SMS to SMS or push notification on an app, my entire flow should reflect that immediately the moment I change the code. So it becomes a self-documenting flow. And the final piece is, I don't want to sit around maintaining and supporting this application. So once it is deployed, maybe once it goes live in production for the next couple of weeks, I'll focus on making sure that everything looks good. But after that, I want to move on to a different app, right? Maybe solve a different problem. So design for day 100 scenarios where totally non-engineers are operating this application. Maybe there are support engineers who are responsible for this, who does not have access to the code base or have no idea how the code is written, but they should be able to debug and resolve the problems. So again, like going back to this, we looked at all of these things, and this is where we essentially built Conductor. Conductor is a platform for doing service orchestration. It was built at Netflix, has been open source since then. It is under Apache 2.0 license, and it implements some of the traits that we talked about earlier of a well-formed orchestrator. It is a successor to a previous PubSub system that we were using. It was born in cloud, as you are all familiar, right? Netflix is kind of the poster child of cloud, right? It runs the entire stack in the cloud, and it helped us kind of further reducing the coupling between the services, and it kind of does everything that we mentioned. So what does it look like when you think about building distributed apps with Conductor? So of course, Netflix had invested very heavily and has been investing very heavily on microservices. Everything is a microservice. So you start with microservices. You have microservices which are stateless, single responsibility. And oftentimes when you think about microservices, there is a misnomer that microservices have to have um, an RPC protocol that it responds over, right? And that sometimes is a necessity because of the overall fundamental architecture, right? But the services can be operating over REST and HTTP or gRPC, or it could be even a single service worker, right? Which reduces the infrastructure complexity in terms of having to now bring up load balancers and DNS and all of those things. Oftentimes they are written in a polyglot environment. You have a service written in a language that suits the best for what it is trying to do. So take, for example, most of the business logic today's world is probably written in Java or C#. We are starting to see a little bit more Go. But if the service is calling some machine learning model, most likely it is going to be written in Python. If it is very UI centric service, most likely it's in JavaScript, or you could be also using JavaScript stack. Other thing is, you have legacy monoliths which are prime for app modernization, but not there yet. Maybe they are running in data centers. And last but not least is humans, right? Not every service is completely automation. Sometimes you have hybrid nature, right? A very good example here is, let's say I have a video file and I want to do subtitling. If somebody has to watch every frame and write the subtitles, that could potentially work for a 2 hour long movie. But if you imagine, right, if you are producing 10,000 hours of content every month or every year, that's not sustainable, and unless you hire an army of people. So you could potentially leverage AI here, right? But somebody has to make some spot checks. So maybe there is a system where parts of it is completely automated and there is a human in the loop. So you build those constructs, maybe integrate with the UI, and Conductor essentially gives you all the APIs and SDKs to kind of do those things. And And the way it works is, you have the services, you have your monoliths, which is exposed via lightweight conductor SDKs, your microservices that are plugged into conductor as one of the service component. Humans integrations are done, serverless is a first class citizen, and conductor server essentially takes care of orchestrating across all of them. They talk to the server using well-defined HTTP or gRPC protocol. So you can support large number of different applications, and including legacy applications as well as different language runtimes. And conductor then takes care of publishing all the stats as metrics. So now here comes the power of an orchestrator, right? If you think about an orchestrator knows about some very important key business metrics. How many workflows are getting started, and every workflow essentially here is an application flow, right? Like, so in the previous example, when you place a checkout, it's an action that user does. But if you think about, right, it's an entire workflow with its own state management. So it knows how many checkouts are happening. It knows what's the average duration of the entire order delivery end to end, like how many days does it take on an average. um, it knows how many of them are failing. What happens if the credit card payments are failing? You are going to fail the checkout process. It knows that how many of those are failing on a daily basis. Maybe if you are so busy and hopefully so lucky, every second that is happening, right? um, Now, what is an application state? Essentially, if you think about application flow, is nothing but a, a sequence of calls to different components inside it. So it also knows how those are operating, like how many notifications are you sending on a daily basis, how many of them are SMS, how many of them are push notifications, what's the breakdown between iOS and Android, for example. How many credit cards are you processing, how many of them are failing. It knows a very rich set of business metrics, and now it can publish it to an underlying metric system. Conductor is a very plug and play system here, so it can support. We started with Netflix's own metric system called Atlas. um, but over the years, like for example at Orcus, we leverage Prometheus and Grafana. I have seen people using VMware Tanzo, Datadog, and cloud specific metrics integration as well. So all of this goes into metrics there, where the consumer can be both operations as well as business folks. The entire state itself is managed into uh, a set of distributed databases. So server itself is stateless. This is an interesting aspect, right? The job of an orchestrator is to maintain the state, but the orchestrator itself is completely stateless. And what that does is, the servers themselves can go down without losing any state, without impacting the availability. And suddenly, if the workload increases, servers can be scaled out. The entire state is maintained in databases with replicas for high availability, region failovers, and things like that. And also, it goes into archival for subsequent analysis, right? Like ideally, what I would love to do is I would want to get all this, let's say, sticking back to our order management system, all the checkout things into an S3 or an Azure Blob bucket, for example, and run analytics, machine learning pipelines to see, what's going on, if I can train models and things like that. So, this becomes a very rich set of training data for me that is captured like with zero effort by default automatically. And final piece is, we talked about the tooling and operational aspect of it, right? We One thing that we built Conductor with was the UI has to be the first class citizen. So we built a very rich UI that allows you to kind of visualize every execution path, right? So imagine this, right? When you write a code, imagine you could visualize the entire code graph. So that's what Conductor does. It allows you to visualize the entire code graph with complex loops and branches and parallel fork joins and everything else. And what does it do is two things. One, for engineers, when things go wrong, it makes it very easy to find out what's going on, where there's a failure, why it failed. And once you know those answers, you know how to fix. And once you fix it, you can resume the flows where it left off. This is a very powerful thing, right? If you imagine, it's like running your code in a debugger, right, in Visual VS Code or IntelliJ, where you can change the variable and continue where you left off. It's more almost like a tape recorder, right? Like you can pause, resume, rewind, restart, all of those things without having to write any bespoke tooling, custom code, or anything. It just comes out of the box. That makes it much easier. Like any new application just automatically gets all of these things out of the box. So Then going back to the same question, right? How does Conductor help not to build a distributed monolith? So as I said, right, like services only talk to orchestrator and they do not know about the overall state, which means, I can write a simple service and not have to worry about like, what should I call next versioning or any of those things. Um, the application state itself is maintained by the server in a persistent store. So, every time you want to ask a question, how many checkout flows are running? Oh, I can just go to the Conductor server and run an API call or look at the UI, depending upon what my persona is, and find out how many checkout flows are currently in process, how many of them are failing, how many of them are completed, how many completed in the last 2 days, everything. And if those which are in process, I can find out exactly where they are currently in the system, like how many of them are still waiting for shipping to be completed. Um, you are not writing versioning code at the service level, but rather creating different versions of the flow, as I mentioned earlier, which means I can experiment without having to worry about changing the code involving even development teams. And the orchestrator itself is responsible for making service calls, or which means that if a service is down, you can configure retry policies, so server can wait until service is up and running, and will attempt once it is kind of up and running. And for cases where no life happens and there are extended failures that happen, you can just ask orchestrator to retry all over again one more time. It's like, please try one more time, and it will try one more time, and if it's up and running, it'll go and finish the call. And because of this, now you don't have to worry about cascading failures. A service can go down if the flows are not using that service, or until that service call is scheduled. Everything continues to operate normally. When there is a failure in that service, that's where you see a hiccup, and then things kind of move normally, right? But backups are done at the server level rather than like individual apps having to maintain this. And again, going back to the point of single point of failures, right? The queues that Conductor uses are fully distributed and persisted. So as I mentioned, servers can go up and down. And again, it's a fully polyglot development environment. We have users on Conductor. To be honest, we started with Java, but then it moved on to supporting pretty much every major language. And Conductor is not just for sequential flows, right? Your application flows are not sequential. Most likely, there are complicated, conditions and situations inside it. So Conductor allows you to kind of build flows which contains, similar to how you write your code, right? It can do things like decisions, loops, fork joins. You can run things in parallel. You can run massive parallel forks, right? Fork out thousands of processes or service calls independently. It can also do retries, as we talked about. But the other important part of an orchestrator and Conductor is that it can actually handle things like timeouts. What happens if let's say you send a message to credit card processing system, or a component, right? The component gets the message, starts to process, and dies. Now your message is kind of lost forever, or not. Conductor will retry after the timeout occurs, which means it gives you at least once delivery guarantees. And when things are not idempotent, you can leverage your application's own database to, or the component's own small database to kind of see if it's a redelivery, and then take the appropriate action. Other thing is that when things fail, it can trigger other workflows to kind of do, say for example, compensation. So take for example, let's say you have charged the credit card payments and everything is done. The shipping has been scheduled, and there was a problem. Maybe there was a natural disaster. The shipping kind of container got lost or something. Now what do? You can kick off a compensation workflow that could potentially go and reverse the charges, maybe issue a refund, maybe redeliver the order with some discounts and things like that to make the customer happy. You can do all of those things in Conductor. And if you notice, right, like you are writing code as if your code has superpowers, as in it never fails, it can scale infinitely, it doesn't have to worry about failures, timeouts, retries. You just write the code. the orchestrator takes care of everything else, and that is significant advantage when it comes to time to market, right? You can easily write and build new apps. You can quickly change your applications without having to worry about what is it going to do to my overall business metric, because I can version it, test it, and roll it out. And when things happen, when things go wrong, conductor gives you ability to kind of look at exactly which task failed. So like I could have a application flow with hundreds of tasks in it, and if one of them fails, I can visually see exactly which one failed, why it failed, what were the logs. I don't have to go and log on to that machine or go to another system and look for the logs and things like that. So that all kind of makes it much easier with conductor. And as I mentioned, right, by the way, the diagram on the left hand side is a real conductor workflow, and that's exactly the kind of workflows that you can build. And you can write services in conductor using conductor's very lightweight SDK. So you can wrap around your existing code base. And here are some of the samples, right? It's pretty straightforward. You never have to import custom libraries, frameworks. One thing about conductor is that it works with your language, with your framework, right? So if you're using Java and Spring Boot, it works with Spring Boot. If you're using Python and Django, it works on that one. If you're using Golang and you are following certain libraries in Golang, it works with those things. And as I mentioned, right, like every service, you can define its parameters around, like how much to wait. You could have a service that waits. Let's say you are building a new application that waits until the Christmas evening and sends out notifications to your customers. You can kick off those things sometime a few days in advance, and it will wait until 24th of December, and then it will go and start to schedule those messages. So you can do those things with conductor without having to worry about writing distributed crons and things like that. Another thing is, as I mentioned, right, beyond retries and timeouts, conductor also takes care of doing rate limiting for you. And this has, of course, as you could imagine, has come with an experience of DDoSing our own services. So imagine a situation where you have, let's say, going back to the inventory check system, right? Let's say it's running on a database. A database can only handle 100 requests per second. Beyond that, it's going to create issues. Database is not yet upgraded. It's in the plans, but not there yet. What happens if somebody issues a massive 1,000 requests? You're going to bring down database, right? You're going to bring down the application. How do you defend your system from something like that? So with conductor, essentially, you can specify the rate limits and say that, like, only send, let's say, 100 requests in 1 second window. You could send 1,000 requests. The 900 requests will get queued up and will get scheduled and executed as their turn comes. So as I said, right, you write code as if your code has superpowers. It just runs. It can scale infinitely. Reality is not that, and that is where conductor helps you kind of do all those things. We have about 12 minutes. I would definitely like to take spend some time on answering the questions. But this is kind of a high level architecture of conductor. As I mentioned, right, like at the heart of conductor, there are three main things. There are a set of distributed queues. There is a state machine evaluator that is responsible for actually running your workflows and applications. And you have set of integrations. No application is an island. You always integrate with systems. So conductor has a very rich ecosystem of integrations that allows you to integrate with multiple different systems, which are cloud specific, general purpose, and so forth, including messaging, including storages, metrics, and all of those things. All right. So enough about all of these things. How do I get started with Conductor? As I mentioned, Conductor is an open source project. So you can look up on GitHub. And if you do tend to visit, please give us a star. It definitely helps creating the visibility. Spread the word. Conductor, if you want to run Conductor, try it out. There are multiple models. You can of course check out the project. We publish container images as well, so you can give them a try. We have a community on Slack, which is pretty active. So if you have questions about how to run Conductor, what are models on which you can run Conductor, what are the use cases for Conductor, or maybe you got stuck somewhere, right? Hey, I have a question. Happy to be there. We are typically on Slack all the time, so we can answer the questions there. And if you want to run Conductor, or if you don't want to run Conductor but want to use Conductor, Orcus, we basically created Orcus, which provides cloud hosted version on various cloud environments including Azure. So check out orcus.io, and you can find more information about how we do that, our customers, and so forth. And if you want to just give it a try, we have a playground. So you don't have to install anything. You can just check it out and play around with Conductor. That's at play.orcus.io. So with that, I think there are a couple of questions from the audience right now. So one is, how does this compare to Ansible Tower? To be honest, I'm not very familiar with Ansible Tower. Sounds like, looking at Ansible, most likely it plays into the infra orchestration. But to be honest, I don't know much about it. So any answer that I give you is going to be very speculative here. I can do some research, and if you want to join on Slack, we can chat there, and I can give you more details there. The second question is, are there observability tools for non-engineering stakeholders? What, where are they? That's an awesome question. So when we built Conductor, we had a total of 3 different personas in mind. We had product managers and the business stakeholders, and I'm going to combine them together because PMs typically get requirements from the business stakeholders, and depending upon what part of, for example, Netflix you are, this could be folks sitting in Los Angeles, responsible for content production, or this could be folks in South Bay here, looking at how do we kind of improve, for example, member notifications, right? So those are kind of stakeholders. Their metrics are different. If you are in the content production, for example, you are more interested in what are the efficiencies that we can gain, what's the cost of building a new tooling for, let's say, content QC or subtitling and things like that. And PMs are working with them, right? So that's one group of users. Second is engineers, and third is basically people who are finally running this in production environment, right? Are responsible for day-to-day life with this one, which is the operations. So the UI for Conductor is where it solves the first and the last set of audience. Of course, it is also for engineers, but how it helps them, for folks who are, let's say, on the business side, it allows you to create dashboards through your metric system. Or what I've seen is also using Conductor data to kind of create a very specific business specific dashboards. Then they can also look at what my overall process is. So if I am responsible for, let's say I'm a PM in the order management system, I want to see what's my checkout process looks like. Conductor kind of gives me that visibility into, as I mentioned, right, what's happening with the orders, like how many orders we are placing, how many are failing, what's the average duration of order, what's the average duration of a shipping with provider A versus provider B. Those things are available in Conductor through metrics as well as in the UI. The final piece is on the operation side. Their interest is more like, hey, there is a customer complaint about order not delivered yet. What's happening with that order? I can just go search for that order ID, bring up the order and see exactly where it is stuck. And if that seems to be an anomaly, maybe I can kind of escalate this to kind of the level 2 support. Or maybe if it is something simple and I can resolve it myself, I can do that. and move on. So those are kind of some of the observability tools for folks who are not engineering stakeholders. Seems like we have one more question. um, I think there's one more question around, can I use Netflix Conductor on premise based on scenario synchronous Salesforce DB? Yes, absolutely. I mean, as I mentioned, right, Conductor is completely open source. With Orcus, we provide production hardened deployment binaries that you can leverage it to use it on-prem, as well as on-prem as in data centers, in your private cloud, or in the cloud environment. Um, there's one more question, which is Ansible Tower. Okay, it can be used to deploy microservices and configure them. So that's an interesting point. Conductor is a very general purpose orchestration system, so it can do pretty much anything that requires you to maintain a flow, maintain the state, and execute on them, right? When we were building our own cloud offering, so when you think about provisioning any cloud environment or any application, right, there are a few things you have to think about, right? So imagine, as a customer, you go and say, I want a new instance of Conductor running in Azure. What happens next? We have to go and configure the first of all, we need to kind of get some permissions from you. Let's say if it's running in our environment, then the first thing that we need to do is we need to kind of provision the underlying databases, right? So I'm provisioning, let's say, Postgres, I'm provisioning Redis, I'm provisioning a few other things. We need to provision, depending upon the size of the cluster, other resources, right? VMs, for example. Then we need to deploy a Kubernetes cluster, which is what we use, or maybe configure AKS to do that. Then we kind of query our system to find out what's the current production release version and what is the current container tag for that. Get that container deployed. While that deployment is happening, in parallel, we configure a certificate, we provision a DNS. Once it's all done, we configure a load balancer and all the other necessary infra. So you can see, right, it becomes a lot more complicated very quickly. In the end, once everything is done, you wait for all these things to complete. Certificate provisioning takes usually a few minutes, sometimes more than just few minutes. So you are kind of constantly checking every few seconds to see, hey, if my DNS is now ready, is my certificates are all provisioned, they are all propagated or not. And once it is all done, you run a small test to verify that, okay, everything looks good, everything is connected end to end, clean up, and your environment is ready. This whole thing is done through Conductor. What we have done is that we have operators that we have created on Kubernetes and workers that can do all these individual tasks. And now imagine this, right, that if I want to deploy this on-prem, it's similar flow, except that, instead of using Azure to kind of configure a database, I'm using some other system to kind of do that thing. So now I can pretty much reuse these things across multiple clouds, different environments. I can change the shape. I can look at it and say, how can I improve the speed? So to be honest, very first version that we had was everything was sequential. It used to take 15-20 minutes to provision one environment. And we looked at it, figured out what can be running in parallel. We changed our workflow. And we went from few minutes or even few hours, for example, at some point of time, to literally few minutes, right? Literally within under 5 minutes we can provision a new environment. So yes, from that regards, it's similar to Ansible Tower, but it's a lot more general purpose. I would say in some ways a lot more powerful. Awesome. Looks like we are almost at the end of the time. So yeah, I highly recommend, if there are further questions, please do join us on the Slack. Visit the GitHub. Happy to answer any more questions that you might have, and hopefully we'll see some of you online.